Section 3.10 Evaluating Properties of Liquids and Solids. Previously, thermodynamic property tables were used to evaluate the properties of saturated mixture and superheated vapor. In this section, we are going to evaluate the properties of liquids and solids. So we know that both liquids and solids are nearly incompressible. The change in density or specific volume with pressure is negligibly small. So on the temperature and specific volume diagram, superheated vapor region is here. On the right hand side, from the saturated vapor line. The saturated mixture is inside the vapor dome. And the left side of the saturated liquid line is the compressed liquid region or subcooled liquid region. Thermodynamic tables for compressed liquid water is in table A5. Table A5 shows the properties of compressed liquid water at various pressure 2.5 megapascal, and temperature is in the first column, 22 saturation temperature, and specific volumes, internal energy, enthalpy, and entropies are shown at different pressure and temperature. So the best way to determine the accurate property values under compressed liquid or subcooled liquid is to use the property tables. But this is the only tables available for compressed liquid in our textbook. So we do not have a property tables for other compressed liquids. They are not commonly available. So then how do we evaluate the properties of liquids without the thermodynamic property tables? There are two other methods to evaluate it. First method, property approximations for liquids. So properties of liquid are not strongly dependent on the pressure. So the compressed liquid is often approximated by the saturated liquid. So we treat the compressed liquid as saturated liquid at the given temperature. So on the TV diagram, the red dotted line is the constant pressure line. And this is the compressed liquid or subcooled liquid regions. Let's take a closer look at this area. So this is saturated liquid line, and this is constant pressure lines. So at a given temperature, compressed liquid state is here. And the saturated liquid state is here. So compare the specific volumes between the two states. There is a small difference in the specific volumes between the two states. We have the tabulated data for the saturated liquid, so we can determine the specific volumes at the saturated liquid. Let's say we don't have the property tables for the compressed liquid, so we cannot determine V directly. So this is the exact value we want to calculate, but since the table is not available, we are going to use the approximate values at the saturated liquid state. So we treat compressed liquid as saturated liquid at the given temperature. So the specific volumes and the internal energy in the compressed liquid may be approximated by the saturated liquid state. And the enthalpy is sum of the internal energy and the pressure times specific volumes. So the internal energy and specific volume may be also approximated by the saturated liquid. Instead of internal energy, we can express the relations in enthalpy at the saturated liquid. We add P saturation times Vf subtracted by P saturated Vf plus PVF. So this term is enthalpy at the saturated liquid, and this term Vf P minus P saturation pressure. That's how we got these equations. Second method is incompressible substance model, and we are not going to use the property tables. We just learned that the specific heat at constant pressure is typically greater than the specific heat at constant volume. It's because the additional energy is required to do work against the pressure. For an incompressible substance, the constant pressure specific heat is identical to the constant volume specific heat. So we use the specific heat C without the subscript. CV is defined du over dt when the volume is held constant. For incompressible substances, the volume change is negligibly small, or U internal energy is independent of specific volume. So CV can be defined as du over dt. So partial differential is replaced by the ordinary differential. So U is only function of T, temperature. In thermodynamics, it is usually the change in the state we are interested in. So the change in internal energy between the states 1 and 2 is shown. From the definition of constant volume specific heat and with the assumption of incompressible substances, CV is du over dt. So du equals CV times dt, integrate over T1 and T2. If the specific heat is assumed to be constant, then the change in internal energy between state 1 and 2 equals specific heat times temperature difference between the two states. Specific heat may be assumed to be constant unless the process occurs over a wide range of temperature. Similarly, the change in enthalpy between state 1 and 2 is shown from the definition of enthalpy. Enthalpy change between the state 1 and 2 equals the internal energy change plus PV. With the incompressible substance models, the internal energy change is integrations of C dt over T1 and T2. And if the specific heat is constant, the change in enthalpy between the state 1 and 2 equals specific heat times temperature difference plus specific volume times pressure difference. Let's take an example. Determine the enthalpy of water at 10 megapascal and 100 degrees Celsius. We are going to use three different methods to determine the enthalpy of water at the given condition. So first, use compressed liquid water table. Pressure is given 10 megapascal and temperature 100 degrees Celsius. So this is the table for compressed liquid water. So at the given conditions, the enthalpy is 426.50 kilojoule per kilogram. So if the compressed liquid table is available, use it. Since thermodynamic property tables are generated from the experimental data, it gives the most accurate data. If it's not available, we'll need to take different approaches. The second method, use saturated liquid data. So the enthalpy in compressed liquid state will be approximated by the saturated liquid state. From table 8.2 shows the saturated water tables. At 100 degrees Celsius, the enthalpy at saturated liquid is 419.04. As you can see, there's a slight difference between the enthalpy in saturated liquid and compressed liquid states. And lastly, we are going to use the following equations. So enthalpy is expressed in terms of specific volumes and the pressure. So enthalpy at saturated liquid state 419.04 kilojoule per kilogram plus Vf, specific volume at the saturated liquid state 1.0435 times 10 to the negative third. Pressure is 10 megapascal. So 10 times 10 to the third, and this is kPa minus saturation pressure. Saturation pressure is here. 1.014 bar or 101.4 kPa. And multiply by 1 kilojoule is 1 kPa times cubic meter, 429.37 kilojoule per kilogram. So in the first method, we got 426, second 419, third 429. So if the compressed liquid table is available, always use it. If it's not available, use saturated liquid data or use the appropriate equations to calculate the enthalpy. Example 3.6. 1/10 millimeter of cooking oil is placed in the chamber of a constant volume calorimeter filled with sufficient oxygen for the oil to be completely burned. 0.1 millimeter of cooking oil is inside the chamber. And the chamber is immersed in water bath. So this is the water bath. The mass of the water bath is 2.15 kilogram. For the purpose of this analysis, the metal parts of the apparatus are modeled as equivalent to an additional 0.5 kilogram of water. The calorimeter is well insulated, so there is no heat crossing the system boundaries. Initially, the temperature throughout is 25 degrees Celsius. The chamber and the water both are at 25 degrees Celsius. The oil is ignited by a spark, so it produces heat. When equilibrium is attained, the temperature throughout is 25.3 degrees Celsius. So both water and the chamber temperatures are 25.3 degrees Celsius. Determine the change in internal energy of the chamber contents in kilocalorie per milliliter of cooking oil and kilocalorie per tablespoon of cooking oil. This is a closed system, no mass crossing the system boundaries, and the total mass remains constant. There is no volume change. Water is modeled as incompressible with constant specific heat. Heat transfer with the surrounding is negligible since it's well insulated. There is no change in kinetic or potential energy. System is stationary. So we take the entire water bath as the system. The energy balance on the system can be expressed delta E Q minus W. So delta E energy, internal energy change, kinetic energy change, potential energy change. Since the system is stationary, no kinetic energy change, no potential energy change of the system. The system is well insulated. There is no heat transfer out of the system boundaries. There is no work involved. So the total internal energy is 0. The system consists of water and the chamber or content. So we need to determine the internal energy change of the content. So the change in internal energy of the content equals negative the change in internal energy of the water. Since water is considered to be incompressible, the internal energy can be expressed mass times specific heat of water and the temperature difference. So the mass of the water, including the metal parts within the system, is 2.65 kilogram. And the specific heat of water is 4.18 kilojoule per kilogram Kelvin. And the temperature rises by 0.3 Kelvin. This is 3.32 kilojoule. And the question asks us to determine the change in internal energy in kilocalorie per milliliter of cooking oil and in kilocalorie per tablespoon of cooking oil. So internal energy change of the contents divided by the volume of oil. And 1 kilocalorie is 4.1868 kilojoule. Or (119 kilocalorie per tablespoon).